Good, whatever it is to you. This is additional lecture A on holography for opti505r. And this lecture is a lot of fun. It uses a lot of the concepts that we have developed over the course of the semester. And what I'm going to try to do today is give you an appreciation for holography. And we're going to start off with a historical introduction. So the way holography started was with a problem. And the year was 1947 when electron microscopes were in their very early stages. Now, the reason why one might want to use electrons rather than optical photons is that the de Broglie wavelength of an electron, typically 200 kilovolts acceleration potential, is about 0.005 nanometers. Now, we learned in class that the resolution, the Rayleigh resolution of a system is around some factor close to 1.22 lambda over NA. So with any kind of a reasonable NA, even if that NA is pretty small, this is going to give incredibly small resolution. With the lenses that they had at the time, and not the lenses, but the optical systems they had with the magnetic lenses that focus these electrons, the theoretical resolution of the electron microscopes was about 0.4 nanometers. That's pretty small. However, the practical limit of these electron microscopes was about 1.2 nanometers due to the spherical aberration of those magnetic lenses. Well, there was a Hungarian electrical engineer named Gabor who wanted to remove the spherical aberration to improve the resolution down to fairly close to the theoretical limit with their numerical apertures in order to see atomic lattices. Well, I've got a great reference here, and that's in your notes on the web about the Nobel lecture by Dennis Gabor that was given in 1971. Dennis Gabor, with the material that we're going to be presenting in the next couple of slides, was evaluated for that contribution to science, and he won the Nobel Prize for that. And in 1971, he gave a lecture at the Imperial College in London, and this link gives you the access to that lecture written out in text form in English. And boy, it's really great reading. So Gabor was a contemporary of Bragg, was very familiar with Bragg's experiments. Bragg predated Gabor, of course. But it was, within the same couple of decades that Bragg did his experiments in X-ray diffraction from crystals. And the Bragg diffraction experiments involved, with Bragg's original work, a two-color solution to reconstructing the atomic lattice from the diffraction pattern of the X-rays. What Bragg did is he looked at the amplitude of the far-field X-ray diffraction pattern, and the bright spots in that pattern were used to define an amplitude transmission mask, okay, which was a simple plate with holes drilled into it at the time. The mask was then illuminated by a coherent optical wave and allowed to propagate to the Fraunhofer zone of the mask. Okay, now this is essentially the Abbe theory of image formation, in which the reconstructed image of the lattice, because of the difference in the wavelengths, was at extreme magnification, and that magnification was the ratio of the optical wavelength divided by the X-ray wavelength. So that technique worked. It was basically taking a Fourier transform of the object to get to the far field, like we do from the object to the pupil of an optical system, and then another Fourier transform from the pupil to the image. Except in the Fourier transform from the pupil to the image, we substituted a different wavelength, so we have the extreme magnification between the ratio of the X-ray to the optical wavelengths. However, because Bragg was just using the amplitude information of the X-ray pattern, it really only worked for symmetric crystals. Very few, limited number of crystal lattices satisfied the conditions that were necessary for Bragg, because he wasn't considering the phase of that far field pattern. Gabor recognized the need to record the phase of that far field pattern in addition to the amplitude for his solution to the E-beam problem. He could do a very similar thing to Bragg if he could record that phase information in addition to the amplitude information, and then he could use an optical reconstruction technique similar to Bragg's two-color technique with an optical wave that within the optical reconstruction he could build as lenses to correct the spherical aberration that was present in the magnetic lenses at the time for the E-beam microscopes. So he fully expected to see crystal lattices. So the problem was, for Gabor, how to record the phase. Well, Molly, probably what we should do is zoom in just a little bit on these so the text is a little easier to read. So go in about a factor of 2 or so. That's pretty good. So what Gabor recognized is that he could use the principle of interference as shown on the right. So now this one we're going to want to probably zoom in a little bit more. So just like we learned, I think that's very fine, Molly, thank you. In chapter 4, we learned that 2-point sources produce hyperboloidal fringe patterns, okay? And that was exactly the principle that Gabor used, and he was thinking that he would record those bright patterns of the fringes on a photographic plate. Now, the photographic plate here is sensitive to the bright features of the constructive interference between the two expanding spherical waves. So once the photographic plate was developed, then we could replace the plate into this geometry, but this time only illuminating with point A, and recognizing that this pattern looks sort of like a zone plate where the dark constructive or dark destructive regions where we had a destructive interference here is blocked, okay? And it's only letting through the bright regions which were the constructive interference lines. Then this acts kind of like a zone lens, like a zone plate lens. And what we see when we look back in through the plate is the image of B, just like a Fresnel lens producing an image of the source point. Okay, slightly different geometry, but same concept. So Gabor recognized that he could use the technology of the time, which consists of these photographic plates, and the fact that the crystal lattices only scatter weakly. This is a transmission electron microscope, so the samples were very thin, and the atomic lattice points act as spherical point scatters, with most of the E-beam energy passing through the crystal unabated to produce the reference wave. Okay. Also, you have the interference between each lattice point over here. So this was Gabor's basic technique. And this reconstruction technique at the optical wavelengths, okay, instead of using the E-beam, then we just replace the point source here, A, with, which represents the illuminating wave to the crystal, an optical point source. And now in B, we see a greatly magnified collection of points, which represent the collection of scatter points that were present in the crystal. Okay. So this is a linear process. And in general, the object consists of the collection of point sources, and the reconstruction of the optical wavelengths produced a magnified image of the object. Now, in his day, this is back in 1947, For the E-beam recording system, he just used an electron microscope. But for the optical reconstruction, he actually had to demonstrate the whole thing optically first before the E-beam. And he didn't have a laser. That wasn't invented yet. So he had to focus a mercury arc lamp down to a very small diameter. And the mercury arc lamp was a filtered mercury arc lamp, only letting through one of the narrow mercury arc lines, down to a region of about 3 microns in diameter that illuminated the object. And that produced his object wave. So he actually used an optical point source. And we'll talk about some of the limitations there in a minute of what he had to work with. But trying to demonstrate the whole process optically was rather limiting for him because he didn't have a very coherent source. The 3 microns represented a fairly his limit of the size and limited his brightness because of spatial coherence. And then he had the temporal coherence problems of the width of the mercury arc line. So he had a lot of difficulty, but he was actually to make some pretty interesting results here. He demonstrated his technique, like I said. He wanted to do it with E-beams, but he had to do it all optically first because it was easier to work with the size of things. And these are his first results. So this is the hologram recording on the photographic plate. And this is his object, Huygens, Young, and Fresnel. And this is his reconstruction. You can see Huygens, Young, and Fresnel in reconstruction. So he called this result holo for whole and gram for writing. So hologram represents the whole writing. And what he meant there was that we're not only including the optical, the brightness information, the irradiance of the recording plane, but we're also recording the phase of the information. And that's pretty cool. So if we know both the amplitude and the phase of the optical wave at any plane, we know how to go back and now with our techniques that we learned in Chapter 5, we know how to go back and reconstruct through diffraction propagation the field, the complex field in any plane that subtended the solid angle in the recording process. So that's really exciting. This isn't just a camera. This is really a three-dimensional recording and allows us to reconstruct three-dimensional objects. Very, very ahead of his time. Okay. Well, Gabor never realized his dream of that E-beam system due to the limitations of his source, coherence, at the time. So, it was talked about in a few papers, but it kind of went into hibernation until 1963. In 1963, a pair of investigators in Michigan, Leith-Upatnieks, published a paper on holography using the new instrument at the time called a laser, which had much better coherence properties. And then, after 1963, the field exploded. Okay. Now, Leith-Upatnieks' geometry was a little bit different. In the Leith-Upatnieks geometry, they used, instead of the online beam, like just shooting the beam right through the sample and the reference in the object wave being along the same optical axis, like with a zone plate. And you know what happens with the zone plate. You get these multiple images. You get multiple orders. Well, with Leith-Upatnieks, what they decided to do, and Molly, maybe we could zoom in just on this top part first. What they did was they placed their object in a field in front of the plate, and then their illumination beam, instead of coming right through the object, their illumination beam came off at an angle. So now there was essentially a bias frequency here in the photographic plate, so that when they went to their reconstruction technique, and here's the reference beam into the essentially combination of zone plate lens hologram here, then when you viewed the reconstruction this way, you saw a virtual image of the object without any of these extra order images coming in from the fact that we're just recording the irradiance in the photographic plate. There are the other images, but they're off at different angles corresponding to the gradient equation here. And for example, you'll get a real image at a different angle. We'll talk a little bit more about that in a minute. But the Leith-Upatnieks hologram, which was actually developed under a government program that it actually wasn't released in the year that they discovered it because it was used for reconstruction of synthetic aperture radar data, really revolutionized the field. And from there, holography just took off. And it still is popular today. We have in the Optical Sciences Center several researchers working on holographic displays. Now, let's do a little bit of math. And my reference here is a book by Collier, Burkhardt, and Lin called Optical Holography. Now, holography has been around a long time, obviously, since the 1940s, but really in earnest with the development of the laser in the early 1960s. So a lot of the development in the first part of the class is going to be with respect to this photographic emulsion film where we record the data on the film. So the idea here is that we have laser light, and maybe the laser light illuminates two objects, and then the diffracted waves from scattered waves from both objects is laser light, so we're assuming everything is all coherent. Interferes at the photosensitive medium. And at that medium, we have these interference fringes between the wave fields reflected from both objects. Now, at the photosensitive medium, we're going to model the first wave as U1 and the second wave as U2. And it just has it's a complex number with an amplitude and a phase, A and phi for the respective phases. So if we look at the irradiance at the photosensitive medium, we have the addition of the two coherent fields, and then we take the complex conjugate to get of the addition to get the resulting irradiance. So we have the kind of form that we've seen before, I1 plus I2 plus 2 square root I1 I2 cosine phi1 2. Okay. Now, we assume that the photosensitive medium has this kind of a response where if we look on the horizontal axis, that's the exposure energy, so that's proportional to the irradiance and the time. And then the vertical axis is the transmission after exposure. So as the light becomes brighter during the exposure, it darkens the silver halide crystals, and in development then we see a dark spot in transmission after the exposure. And it has this kind of a curve. We're going to assume that we're on this linear part of the curve here where the exposure is equal to the irradiance times the time. And there's the net transmission then is some offset in transmission minus the slope of this linear region here times the exposure energy. Okay? And so we just substitute in the exposure time times the irradiance, and we have the resulting amplitude transmission of the hologram photographic plate after it's been exposed and developed. So now let's look at that a little more closely here. The field incident onto the plate after exposure and development gives us a transmitted field that is the amplitude transmission that we just derived from the exposure equation times the transmitted field is the amplitude transmission times the incident field. All right, if we just bring that through, we're going to have a DC term due to the residual base. It's called base base transmission, okay, or residual transmission, and then the linear part that we want. Okay, so now let's look at the U minus term, which we're going to take away object 2, and replace the in the same plane the hologram after exposure and development. So we're going to be illuminating the plate with just U1. Now what we do is set then U minus equal to U1, and then U plus is equal to T times U minus, and that's equal to the base transmission, which just follows through. And then we have the irradiance of that was illuminating the photographic plate before development times the slope of the exposure curve times the time of the development times U1. Now when we work these terms through, it's written out for you here real clearly, what we wind up having is a term that is proportional in transmission to the original object wave. That's the complex term of the object wave that illuminated the plate to begin with. All right? So that includes the phase information. Now there's some other terms in there. There's a linear slope term times the irradiance from object 2, which usually these irradiance values are by the time they reach the photographic plate are fairly uniform. So that you can pretty well take as a constant. And then you have this other term that is proportional to the complex conjugate of U2 and U1 squared. Now the important thing here is that the amplitude and phase, which would determine the direction of propagation, right? Because if we have a linear phase term, you're going to propagate at an angle, just like a tilted plane wave. And so that's going to come off at a different angle. And then you're going to have some constant terms in there too. And then you're going to have the attenuated illumination beam in there. Okay? So the point is, we can reconstruct with this recording process the actual wavefront amplitude and phase of that missing object. Okay. So the idea here, very simply, is that if we take away object 2 during the reconstruction process and just use wave 1 to illuminate the hologram, we can look through the hologram, and when we look down at the hologram, we're going to see the original object wave from wave 2. If we back up far enough, if we've chosen our angles correctly, then the straight through wave from object 1 won't interfere with our view of object 2, which is down this way. And we see a true three-dimensional image. All right, now in the notes, what I've given you is several things. I've given you several different recording geometries and several different cases showing how to calculate where the different beams are based on the K vectors. We all know this from chapter 4. So what I'm going to do, the limited time, that's pretty easy reading for anybody that's gone through chapter 4. We're going to skip through that stuff. It's there for your reading enjoyment. And just really talk about holograms themselves. What do they look like? Well, this is a hologram recorded in this way. Okay? And this is a hologram as seen through a microscope. So in that recording plane, the actual hologram doesn't look anything like the image that we view when we illuminate this with that reference beam. Usually the reference beam, and this is expanded upon in the notes that I skipped, is usually either plane wave or a expanding spherical wave. But that complicated object and the interference pattern result doesn't look anything like the object that we're trying to look at, trying to reconstruct. But you get some beautiful results. These are the most elegant kinds of results where this was the object, and this is this is actually just a picture of a beautifully reconstructed hologram. For this particular hologram, I'll show some other examples in a few minutes, but for this particular one, I didn't have a laser to reconstruct it here in the classroom. But there are three objects on a rotating plate. I think this is some kind of a music box where we have a Christmas tree and a rooster and a little girl. And the neat thing about this is this acts like basically it's like a window, a true window, where we look through the window and we see the object in 3 dimensions behind it. So if we change our view angle, here we've got one view angle, here we've got another view angle, it actually looks like there's the real object behind there, like you'd reach out and grab it, okay, because we change our perspective. You don't get that with a normal photograph. Okay, now there are a couple of things to talk about in these extra notes. There are a couple of pages here from Jim Wyant's old class notes. So he basically repeated some of the theory. And there is one thing I wanted to show you, though, with respect to thinking about how large of an angle we need between the object and reference wave, so that if we illuminate it and try to see that missing second object, we don't want to interfere that with the illumination wave coming through the hologram, or with the conjugate order that's produced in this kind of a recording. So maybe, Molly, that's a good magnification there. We've got some spectrum, some angular spectrum of the light coming from the object that we want to reconstruct. And let's say we are recording and reconstructing with just a plane wave. So we've just got a K vector coming in here at a different angle, okay, due to the reference wave. Theta sub r is the reference, and the width of the spectrum coming from the object is about theta r. Or, I'm sorry, theta 0, 2 theta 0. So the spectrum of the object then has this, in terms of spatial frequency, 2k0 sine theta 0. And then the reference wave is offset by k sine theta r. And the conjugate of the reference wave, which produces that real conjugate image, is minus k sine theta r. So if we look at this in terms of the spatial frequency spectrum, remember what we're recording with is the irradiance. So we have to take that complex conjugate, and just like we found with the optical transfer function, we have to take an autocorrelation here to get the spectrum of the resulting distribution. So we have this 0 width spectrum, okay, which corresponds to the light coming straight through the object, and then the offset waves of the true object wave here, OR star, and then the conjugate of the object wave, O star R. And so the point is that you have to have your reference wave at a large enough angle not to interfere with the autocorrelation width of the object in the reference beam. And here the reference beam is just a delta function, but the autocorrelation width then of the object wave, we have to bias our plane wave angle at a large enough angle to avoid that width of that spectrum. Otherwise, we're never going to be able to separate the hologram. Okay. Well, one of the things about this is we need to consider the coherence length of the laser. Lasers generally, and the lasers we use for this sort of thing, really don't have a problem with their spatial coherence, but as long as it's a well-filtered laser beam. But their temporal coherence is a requirement. Now, this is, again, kind of an old slide. This goes back probably before the year 2000, so it's a little bit old on the lasers. There's actually higher quality lasers now. But you can use pulsed lasers like frequency double YAGs, Ti sapphires now, and pulsed diode lasers actually can work under some circumstances. At the time, there was also pulsed ruby lasers. And then CW lasers, of course, helium neon. Argon lasers are real popular. Krypton lasers, and not much anymore, but back then there was dye lasers. Now we can have supercontinuum lasers and all kinds of things to use. The important thing is that the width of the line has to be narrow enough to get our long temporal coherence length, because there's a difference in path lengths between the object wave and the reference wave, and we have to be in our recording plane, the fringes have to have a high enough contrast in order to see the fringe recording with good contrast. Okay, this gives us our best holograms. So let's back out just a little bit. Now this is a different kind of a hologram. This is a hologram that was actually described in a photographic process by Lippmann. And it's elegantly simple. It doesn't, it has some limitations in terms of what you can do with it, but it's actually probably more popular than the original type of hologram or the Leith-Upatnieks hologram in terms of art, commercial art. Where what we do is we take, for example, a mirror surface. Lippmann actually used a pool of mercury, and then put emulsion onto a glass substrate and put the emulsion on the mirror surface so that the light beam coming in was reflected off the mirror, and then the standing waves, which we learned about, if you remember in Chapter 4, that are parallel to the mirror surface, formed a Bragg grating. And then when we illuminate on the Bragg condition, we have a very strong reflection, very high efficiency reflection with the illuminated wavelength. Well, this actually works in white light if the emulsion, of course, has its properties, or we can reconstruct in white light and see some very amazing types of reconstructions where we put the object just above the emulsion and form these Bragg gratings. And I've got some examples of those here in a Lippmann type hologram. And what I need, what I'm going to ask Molly to do is to turn off the lights in the room, and I've got my own little light, which is just a high intensity light. It's a point source light, and or not really a point source. It's just a high intensity light, like you'd see in a decorative situation. I'm going to take my holograms, and I'm going to hold the hologram here. Maybe back out just a little bit. This is. Let me show you first the width. That's the width of the hologram, okay? And this is the hologram. And this is a hologram of a historic timepiece. This is historically the Wild West down here. So I thought it'd be appropriate to show you a 357 Magnum Smith & Wesson. I think that's what this is, okay? And you know, you can see the three-dimensional character. This looks much, much deeper than you know, the thickness of the plate. Okay, it's a very famous Lippmann type hologram, white light hologram, and you can see the bullet there in the lower right portion of the hologram. Okay, and here's another one. I just have a few here to play with. These are, you know, you can purchase commercially. This is well, somebody, a student maybe who spent one too many nights studying late. And again, very thin. Okay, the depth here is amazing. And let's see, here's another one. This is an owl. Okay, you can rotate it around, see the owl. Beautiful. Again, only a few millimeters thick. And here's another real popular one too. That's the thickness, and I believe these are, yeah, it's just a combination of quarters and dimes and nickels and that sort of thing. But it looks much deeper than it actually is. Okay? So this is an example, very high quality example of some of the three-dimensional reconstructions that are possible even with white light illumination. No special laser needed for those white light type Lippmann holograms. Okay. Well, there's also very serious scientific work that can be accomplished with holograms. And we're going to talk about a couple of those. These are still active, and the ability, and we'll talk about this a little bit later in the class, the ability of the newer photographic cameras and some of our interferometric techniques to record phase have caused another rebirth of this type of technology. It's useful the way it is now, actually, for several different applications. But now, with the number of pixel counts and the number of pixels in a camera and the ability to record phase, it's, you know, the potential for this is really amazing. So let's focus in just a little higher magnification there, Molly. That's wonderful, thank you. And here we've got a classic kind of a setup where the laser beam produces a reference wave from a, I'm sorry, this is the object wave from a focused laser beam at a point, illuminates the object. And then we can take a beam splitter and split off part of the beam, focusing it down for the reference wave to record on the hologram. And as we said, the hologram historically has been these recorded emulsions, which still, by the way, produce the highest quality histogram or holograms. But you know, there's the strong potential now for the electronic recording of holograms to be extremely useful and very high quality, given the new kind of cameras that are available. So the first thing that we'll talk about is real-time holographic interferometry, where we make a hologram of a surface and process the hologram, replace the hologram in the original position, illuminate it with both the reference and the object wavefront. So we're basically repeating the exposure process, but with the developed hologram in place. So that's going to produce the same interference pattern at the plane of the hologram. But now if we deform the object, that real-time wavefront and interference pattern is going to be different than the recorded pattern. And what you see is fringes that represent the optical path difference in this three-dimensional image between the recorded object and the deformed object. Okay? So you don't obtain the actual surface shape in the fringe pattern, but what you do is you obtain the difference of the undistorted and the distorted object. Okay. Now here's some examples. This is a cube that was heated. It was an aluminum cube, and it was just heated. So you can see the uniform expansion on the cube surface. Here's a honeycomb, like you might see on a construction panel, between two flat plates. And the one region of the plate was debonded. Now realize how much OPD is there between each fringe is only a wavelength. Okay, remember that same kind of interference equations hold. So this is only a few wavelengths of deformation, but that might be important to indicate, for example, a debonded segment of the panel. Here's some fun ones. This is airflow past a cone. Now this is not Schlerian photography. This is actual holographic interferometry. And then a candle flame, where here what we've done is actually used a laser beam to record the information here with the candle that's where the actual candle light is filtered out. So what we're looking at here is actually just the laser beam, and the heat that's generated from the candle, in this case, distorts the optical path of the air around it, and we see that optical path difference in the distorted hologram. And here what we've done is, from airflow through a wind tunnel, shown the pressure waves associated with the airflow past the cone, which changed the optical path by the air density, so temperature and density. And here's a similar kind of a picture with a light bulb, where I'm not sure what the difference in the temperature field is, but these are two different temperatures of the light bulb. And, you know, you can use pretty rough objects like this is a tire, an automotive tire, which has some defects in it. Okay, now that's two exposure holography. You can also think about moving objects. Okay, so the idea here is to look at an object that's moving, and it turns out that you have to have some restrictions here. The vibration amplitude shouldn't be more than a couple of tens of wavelengths. We'll talk about why in a minute. And the hologram has an image that has interference fringes superimposed upon it. The fringes are contour lines of constant equal vibration amplitude. So here's the experiment where we take a vibrating plate, and it has a cosine kind of oscillation here, very simple. And we record the oscillation over some time interval t. So this is the normal exposure that we had before, but now it's changing a little bit because the object wave has a phase difference. Remember, we're working in reflection here. So we've got a factor of 2 times k times the physical displacement as a phase change in the object wave. We're assuming that the amplitude of the oscillation doesn't change. It's just the phase that changes due to this distortion here. Okay? And then we record that same interference that we had before. We record the radiance, but that is averaged over time. Okay, well, if we look at just that phase term, we have an e to the j delta, and that delta includes a cosine, over omega t. So that's a J0 Bessel function, where the argument of the Bessel function is just k times the displacement, optical displacement, 2 times the physical displacement. So if we look at the irradiance then of that observation point, that irradiance is going to be proportional to the Jz Bessel function of that displacement argument squared. And if we plot out that J0 Bessel function, we see that that goes to 0 at regular intervals, okay, proportional to the displacement here. This is the phase, 2 pi over lambda times 2 times the optical displacement, 2 times d. It's reflection, remember, factor 2. Okay, so when we look at one of these things, we see high contrast fringes where the zeros are on this first 0 of the Bessel function. And then lower contrast fringes, of course, you can see this contrast reduce the amplitude reducing there. So your amplitude changes of the recording, the reconstruction. So we get a ring pattern that's proportional to the vibration. And there's several examples here where we look at different modes of vibration on a vibrating plate. You can do this, again, it's holography, so you can do it on all kinds of different objects, rough objects. Here's a guitar. The story that goes along with this, when I was a student, there was a student in another group who had access to some of these high-power pulsed lasers. He asked Yamaha if he could evaluate some of the guitars. Yamaha sent him the guitars. He did the evaluation in this kind of a mode, sent the results back, and they gave him the guitars. So I don't know. Maybe it's a good way for a student who likes music to con an instrument company into some nice equipment. Okay, so that brings us a little bit close to the end here. Let's back up a little bit, Molly, and talk about what is state of the art. Well, it turns out that the photographically produced and recorded holograms are the highest quality still. Okay. However, they're mainly used as art pieces. Now, there are some scientific applications that we talked about here. There's kind of a gray area between diffractive optical elements and holograms that are used in optical testing for large mirrors and such that are kind of like holograms, or more like, to me, they're more like zone plates than holograms, but one is kind of an extension of the other. But mainly for these, three-dimensional, very pretty things like I showed earlier in the lecture, those are primarily art pieces. However, the resolution and the pixel count of today's digital cameras, along with low-cost computer processing power, offers us the opportunity for digital holography. Okay, now that gives us some exciting applications, really. Okay, and biological imaging, for example, these techniques are being investigated, and so here's a picture from a journal article. I've given the reference here. It was just, well, it was 1998, but there's been more work on that since then. This shows the basic technique. Where here's a specimen, okay, and you've got a laser beam coming in here. This happens to be an argon laser at 514, kind of a powerful laser at a watt. The reference beam comes through here to a beam splitter, and you know, I never noticed this before. Oh, okay. Actually, the reason that it's so high powered is there's a couple of splits. I first want to talk about this line that goes up this way, and it comes over here. This forms the reference beam, okay, off of a PZT mirror. And the reference beam comes up here and then illuminates the sample as a plane wave. And then the object wave comes up here and illuminates the specimen. Of course, this is just a schematic layout. The angles are different according to what we talked about earlier to separate the angular spectra. But then an objective lens picks up the diffracted wave from the specimen, which could be a very low contrast kind of phase object like biological cells. And then that spectrum of the scattered object wave comes back through this beam splitter and interferes with the camera. Okay? So we have our hologram on a CCD that in this case it's only 512 by 512. So that's really not all pressing the resolution very high. This has another couple things here to talk about. It has a PZT mirror on it. Now remember I said that the whole reason Gabor wanted to play this game with the interference and use zone plate-like reconstruction on his photographic plate was that he couldn't record the phase with the photographic plate. Well, you've seen from Jim Wyant's lecture that, darn it, all we have to use is phase shifting interferometry. We can also use the 4D camera that they have to do that in real time. This doesn't use that. This uses actually phase shifting here. And we can get the phase directly along with the irradiance. And is that cool or what? Then, after we know this is the information in the pupil. We can use Fresnel or Fraunhofer transformations, like we learned in Chapter 5, to reconstruct a three-dimensional volume of the object, because we have all that information. Is that cool or what? Okay, now this system actually has another path here, which actually picks off a piece of the reference beam and comes back and interferes a plane wave with a plane wave to produce straight line fringes. And there's another camera here. And what that's used for is called a fringe analyzer. All that does is just control the PZT to give you a known amount of shift, okay, which is kind of a problem with PZTs, which is what Jim talked about. But this is actually kind of old school with respect to the interferometer. You guys know from Jim's lecture, the state of the art is this 4D real-time interference. And actually there's a project that 4D is working on right now that I know about where they're trying to use this for this kind of an application. Boy, is that exciting. Okay, so other modern applications, security tags, Visa cards, monetary notes. You've all seen the little dove on your Visa card, hopefully. I met a guy whose company actually does that. He attended our workshop last year from Columbia. And his company manufactures those little tags, security tags for monetary notes. Several countries use holograms on their monetary notes. Optical testing, I alluded to this a little bit before. The Jim Bird's group here, his group is famous for testing secondary astronomical mirrors and aspheric mirrors with, well, you could call it a hologram. I kind of call it a zone lens, but it's all in the same family. And then there's computer-generated holography. Okay, now what I'm going to show next is, I'm going to talk through it also, is a movie clip that was actually produced by a couple of junior undergraduate students, Sam Martin and Davinia Fleming. And they did this, this is actually a part of their video for a class last year. It was their lab class 380A. What I had the students do is their own video lab project report. They did an excellent job, along with most of the students in the class just did an outstanding job. And I'm going to show a little piece of that clip now, along with my explanation of one of the techniques that we use to make these holograms now in the computer. So what I've got, hopefully, on my laptop, let me just bring up my system here. Okay. So we've done this, done this. Now I'm going to be talking about something called the Gertzberg-Saxton design algorithm. And what we have here is a lens. And in the front focal plane of the lens, we're going to put our hologram. We're going to learn how to make this hologram. Because what we want to produce over here at the Fourier plane of the lens, in the back focal plane, is a desired pattern, a desired light pattern. And this Gertzberg-Saxton algorithm is an iterative technique in order to allow us to do that. Now, we want the CGH to be very high efficiency, so we're only going to allow the CGH to change the phase. One of the things that we've done in the last few years is to be able to make these arbitrary phase profiles by laser writing into photosensitive material, that photosensitive material having a topography that's proportional to the laser exposure. So we can change the phase and transmission by the depth of the material through a computer-controlled laser writing process. But we still have to design what we call the computer-generated hologram here in order to produce an image. Notice that this is not an imaging geometry. This is a Fourier relationship between the CGH plane and the illumination pupil. So this is actually the way they make, one of the ways they design laser pointers. So we start with a random phase diffuser, and we multiply that by the object that we want to produce in this pupil plane. And for this case, I chose Wilbur the Wildcat, our school algorithm. We inverse that inverse Fourier transform that multiplication to the CGH plane, discard the amplitude and set the amplitude equal to 1, but keep the phase information. Then we take a Fourier transform of that phase-only result to the pupil plane. And in that plane, we again disregard the amplitude information, keep the phase information. We force the amplitude information equal to the desired pattern. And then we cycle this back and forth maybe 40, 50 times until it converges on the phase-only distribution that we want. Now, a consequence of using the random phase diffuser is that we're going to have some speckle in the image. You guys have probably seen this with laser pointers. The clip I'm going to show next is from Davinia and Sam of our Wilbur the Wildcat school hologram, or school mascot. And they actually made this on a grayscale hologram.
Using the same setup as the diffraction lab, we placed our hologram in front of the laser source and used the attached webcam to view the different diffraction regions.
We started with the camera focused on the hologram surface where we can see the Fourier transform that was encoded onto the material. As we move the camera back along the optical rail, we see the Fresnel region where light is diffracted in a non-recognizable pattern. This is the area where we have a Fresnel number greater than 1. The Fraunhofer, or far-field region, is regularly located far away from the hologram. An imaging lens brings this region back to the focal plane of the lens. It is here we see our final image of Wilbur.
Okay. They did a great job with that. So that's a brief introduction then to holography. It's a great subject. And with modern cameras and techniques, it has a lot of potential. So thank you very much. That's the end of this lecture A.